Oh, I didn't realize I had such a great fan club. Thank you so much. No, I'm very pleased to welcome all of you to, I think, what will be a very intriguing and thought-provoking session looking at should technology advances drive decadal survey science or vice versa. I think it's been my personal observation and the observation of others that I've spoken to as well, that there's been the perception that when you look at the scientific decadal surveys, that many of the highest priority recommendations have been driven by the fact that the missions that have been proposed have not really proposed any new technology or were deemed technologically ready. And it's interesting to compare that against what's happening these days with technology capabilities and advancements and the role that these new approaches could have to help drive scientific thinking and potentially new, even more transformative ideas. So this is really the question that we want to try to explore in the panel. And I have a really wonderful set of panelists that I'd like to introduce to you now. So I'll begin, why don't I begin with the order on the screen here. So Harriet is the Executive Director of the Keck Institute for Space Studies at Caltech, just at the end here. So the Keck Institute is a think and do tank that brings together scientists and engineers to develop innovative new space science missions and technologies. And before joining Caltech, Harriet was head of market analysis and business intelligence at the European Space Agency with the Connectivity and Secure Communications Directorate. And next, Adrian is the principal investigator of the plasma instrument for magnetic sounding on Europa Clipper at Johns Hopkins University Applied Physics Laboratory. She's a planetary scientist at Johns Hopkins APL with over a decade of experience with interdisciplinary research, laboratory work, and science missions. And Adrian's worked on NASA's Cassini and ESA's Rosetta missions, and was also part of the Trident Phase A discovery concept and study. Miguel San Martin at the end of the row here is an engineering fellow of guidance and control at NASA's Jet Propulsion Laboratory. Over his nearly 40-year career at JPL, Miguel's contributed to the Magellan mission to Venus, the Cassini mission to Saturn, and served as the chief engineer for the GNC subsystem on the Mars Pathfinder mission, the Mars Exploration Rovers, and the Mars Science Laboratory. And Miguel was actually a co-lead of the technology chapter, Chapter 21, of the recent Planetary Science and Astrobiology Decadal Survey. And Thomas, who's just sitting right here on my left, is a professor and director of ETH Zurich Space. Previously, he was the longest continuing running head of science at NASA from 2016 to 2022, responsible for 130 missions with 37 launches, including JWST, Parker Solar Probe, Mars Perseverance. That, of course, included the Ingenuity helicopter. And he was also founder of the largest entrepreneurial program at the American universities at the University of Michigan Center for Entrepreneurship. So these are only very brief introductions to this distinguished panel. I really encourage you to go online and to read a lot more detail about their backgrounds. But now, just getting into the session a bit, I wanted to put my first question here to Thomas. So, when looking at the decadal surveys, there are many, high priority recommendations that they have to account for when the missions are developed and executed. And it's a very complex effort. So I was curious in general what your feeling is on how we've done so far.
I appreciate the question. To a certain extent, we have to remember that the practice of decadal surveys came from astronomy and astrophysics, where the idea really was that you could only afford one big facility per decade or so, if you were lucky. Perhaps it took a little bit longer. But it needed to be absolutely clear what the highest priority science was. So kind of, if you want the function of all decadals, is to prioritize science against science. And I think in that realm, the decadals have done really well. So kind of, I've been both part of decadals, but also I've been part of the executive leadership team at NASA. That really helps to walk into an office and say, look, here's the highest priority. It's more important than the other things because the Decadal said so. That, by the way, has given continuity to science missions, especially when I got into trouble. And it also has, has really helped organizations go forward. So from that perspective, I would just say as an AA of science, that was the most important ingredient from the community, bar none. Without it, I actually wouldn't know how to do the job. Mm-hmm. Okay? Because it's not the last idea you heard that's good. It's the idea that went through that. I think that vetting process, the deep vetting process that the Academy does, I think there are challenges with Decadals, and you mentioned some of them, and we're going to talk more about it, but I just really wanted to point out the tremendous value of the Decadals, kind of from the point of view of helping prioritize science against science.
Mm-hmm. Yeah, I mean, we've seen many of the fantastic results from these missions, from the planetary science, the astrophysics, heliophysics missions. The results have been really tremendous. So I would agree. I think we've done spectacularly well, but there's always room to look at, what more could potentially be done if we have, the most ready capabilities that could enable even more ambitious work to be proposed. And then that's something that I'd like to address with you a little bit, Adrian, because the decadal process in general is a very collaborative one that we know, and by its nature, it does drive the community to prioritize science. But as I was mentioning earlier, it comes at what I would consider generally the viewpoint that you want to prioritize the highest science you can do, but use the lowest risk approach that is necessary to ensure that you get selected and that your work is deemed feasible. And even at the extent of really focusing more on these high heritage capabilities to make sure you can find success. So I was curious on your thoughts regarding if we're going to try to look at more ambitious science questions that would require more substantial new technology development. What are your thoughts on how we should go about doing that? What are ways in which we can engage the community to think about new technology capabilities that could help us do even more ambitious science?
Yeah, so I obviously come at this from the scientist perspective. So, the most exciting science absolutely has to be the highest priority of the Decadal Survey. But we also must remember that the time frame that we have to do this science is 10 years. It's not a lot, not terribly a lot. So where my concern comes in with the development of substantial new technology at the stage where these concept studies are submitted to the Decadal panel is that we know that there are challenges and things happen and there are difficulties and there are increasing needs pretty much every time, but more so for new technology. So that obviously comes with a cost growth, and when we have a cost growth or end up with one big mission that then ends up eating up the budget, we mortgage the next decade, the next decadal. So that limits science because now we have less opportunities to explore a more diverse list of targets, and typically the more diverse targets, the more science we get out of it. So I'm not sure if the decadal recommendation is necessarily because there is a perception that the high heritage and low risk missions will be more likely to be picked by NASA, but instead maybe it's more the desire to achieve the most amount of most exciting science within the 10 years that we have. Right. So that requires technological realism and to some extent economical realism. And of course, we do want to explore new technologies, and I think we need to do a better job in connecting the scientists with the new technologies, or if there are any processes happening at NASA to develop new technologies, the scientists need to know about it. But we need to start this process way ahead of when the Decadal panel gets together and when these concept studies are submitted. And we need to be very strategic about the concept studies, and of course, that would require probably a substantial amount of investment, so we need to be strategic with our investments. And so by the time the concept studies that require or use new technology and get to the Decadal, those were more likely to close technology-wise.
Yeah, I mean, a number of us have contributed white papers to Decadal science teams, and we know the important role that they have for the concept studies and the impact that they have. But even still, if I look at the recent Planetary Decadal for Uranus Orbiter and Probe, it's very explicit. You know, it's the highest priority recommendation because it was deemed not to have any new technology requirements, and it was deemed technologically ready. And it's just, you know, an interesting process to consider from the community perspective of what they want to achieve scientifically, if that was an overriding factor to drive the science, and how the community thinks about the potential role that technology could have for other questions that they may want to address, which would also be deemed favorably by the National Academies teams. And it leads into actually a question I wanted to explore with Harriet a little bit, because you did, Adrian, talk about the nature of how you bring the communities together to think about these types of things. And from my experience working on some of the white papers, it's a little bit ad hoc. Not that there's anything wrong with that, but it is a little bit ad hoc. And I know, Harriet, within the Keck Institute, you actually have mechanisms and processes to bring together a variety of individuals in a setting where they could think in a very explorative fashion about the future types of ambitious and challenging missions that would be of great scientific and technological interest. So I thought you could comment a little bit on what potential role think tanks of that nature could have to help garner the community to look at the full breadth of capabilities that they should consider when thinking about what the next set of transformative science missions should be.
Of course, thank you, Charles. So it's a really interesting question. I want to build a little bit on what Adrian was saying about that role of how do you maximize the science return in the Decadal Survey. And I think technology advancements can be a real enabler of that. It's about finding the right balance between the two and bridging the gap between the science and the technology communities. And that's something that we really look to do at the Keck Institute for Space Studies. We really look to build those communities, develop ideas that have the opportunity to develop those revolutionary science and technology capabilities by building those communities, bridging those gaps, and also empowering space leaders of the future as well. So since our founding in 2008, we've organized over 100 different study programs that have brought together representatives from over 300 different organizations from 30 plus countries. So we're really looking at having that broad reach across different science, space science and technology domains. And that really is looking to help advance the science case for space missions. It's looking at feeding into and supporting the decadal process and also driving space policy priorities as well. I think one of the key secrets to the success and the impact there is really about fostering that interdisciplinary collaboration and bringing scientists and engineers together to understand the trade-offs and the ways that we can balance those priorities across those different domains. And I'll give maybe a couple of quick examples just to showcase that. So we had a recent study, we've just published the report from a study in 2022 that was looking at fast response missions. So understanding, again, bringing together the science community with the engineering community, understanding what architectures are possible for rapid response missions to near-Earth objects, which has ultimately led into a recommendation in the Decadal Survey for a future mission along those lines. And then maybe an example which is maybe near and dear to your heart, Charles, given that you were one of the co-leads of the study. In 2012, we had a group come together, again, scientists, engineers, program managers across the different areas of the space science and technology community, looking at the role and the opportunity for small satellite platforms for space exploration. And that's been really pioneering in terms of some of the science that's been able to be delivered through these new platforms, which I think we maybe take for granted today in terms of what has been done, but really seeing those early stage ideas as a real catalyst to enable and pioneer the use of new technology that then can be fed into the decadal process and help support those science objectives in the future.
Yeah, in fact, I really enjoyed Sir Martin Sweeting's talk earlier today about the historical timeline that small mission development has played in his work and what it's meant for exploration in general. And incidentally, that's how I actually got to know Thomas quite well, because that led into a National Academy study Thomas at UCO led with Pavia Law, looking at whether or not you can actually even achieve significant science with these other small platforms, which was really a technology advance at the time. So there's a potential future there. Were you going to make a comment, Miguel? You look like you wanted to make a comment.
No, I'm waiting for my next question.
Oh, okay. Well, we can go right ahead then. So actually, you know, I mentioned earlier that actually you were one of the co-leads of the technology section of the Planetary Decadal. And one of my observations has been, for instance, in looking at the astrophysics decadals over the prior years, that they've really been forward-leading in terms of establishing, you know, technology capabilities as a means to drive the types of scientific recommendations that would be pursued, even though, you know, as Adrian pointed out earlier, it's a 10-year time frame. Many of those capabilities, particularly with respect to detectors and other capabilities of that nature, you know, do take a while to get into place. But that's realized, and these decadals are actually now putting together programs like GoMap for the astrophysics to provide mechanisms to encourage specific investment in technology capabilities to help drive science. And I was curious on your perspective from the Planetary Decadal and your own personal experience. Does that seem like a good idea? Is it something that we should be expanding?
Yeah, I mean, my experience with the last Decadal Survey, the astrobiology and Planetary Survey, was that we didn't know exactly what were the missions that NASA was going to, the Decadal was going to recommend. So therefore, we could not target the technology to those recommendations, right? So we had to cast a very wide net, you know, of technologies. And you can never go wrong by saying we want more efficient solar arrays, we want, you know, extreme electronics for extreme environments, you know, and but also there was the opportunity, and we took it of perhaps making recommendations how the process of that NASA should go in organizing, funding and organizing the technology development. I think that we concentrate perhaps more on that than trying to identify what are the actual technologies. And one of the things, for example, that we felt that we could do better is like having better metrics, you know, so be able to say, how are we doing? Are we actually doing well? Or you know, are the investment, you know, the recommendations from the previous decadal on technologies, you know, were they actually you know, carried over or not, or they recommended the wrong technologies. I mean, it's a moving target, right? So it's a very difficult problem. So then there was a recommendation of, well, we need more metrics, you know, to be able to, and perhaps more centralization because there's a very distributed system of technology agencies within the NASA itself. And another thing that I think that we recommended is to have a faster loop, not just once every 10 years have this conversation, actually, because it's a moving target, right? So, and then there is the issue also that that was the biggest challenge of all is that the amount of time it takes to develop technology. So essentially, in some ways, you should be thinking about the technology for the next decadal. You know, kind of like pencils down on technology for this decadal. It is what it is. You know, what missions can you do?
Yeah, yeah. I mean, it's interesting that, you know, the pencils down viewpoint and what missions can you do. I mean, you know, I think from the broad sense of the community, you know, one of the great things about, you know, the decadals in general is, you know, you can do this fabulous science, but it can take many, many years to have these missions come to fruition. And, you know, the number of PI opportunities to lead these things is small. You know, when I think about the technology capabilities that exist now, even beyond small missions and things of that nature, it just seems to me that if we can find a way to get the community to think in terms of how we could execute these high priority missions more rapidly by the use of technological advances, you know, we could increase the rate of science return, we could grow the number and diversity of scientific investigators as principal investigators much more rapidly. And I just think there's room in the process to explore what, you know, technology advances could help drive sort of a new evolution of, is this still on? Yeah. So the new evolution of the rate at which we can do these types of missions. And also looking from the other perspective, you know, are there science questions that we could explore that are still of great value, but could also help us move a little bit more rapidly? So I was just curious in general, you know, the panelists' thoughts on, you know, are there technology capabilities we should start thinking about now that could help enable these things? Or are there, you know, broad science areas that the community should be thinking about which might be able to help advance key technology areas? Like if I were to put out an example, you know, I know some people that have been looking at, you know, gravity probes, which you would deploy around small bodies en masse to try to gain properties of their interior structure. Or even the current work that's going on now and people thinking about, you know, the role that quantum sensing might have for future types of measurements. I mean, I'm curious, do any of you have any knee-jerk reactions?
Yeah, so we actually had one section of the technology chapter was, which I enjoy a lot contributing to, was it was not a recommendation. It was kind of like, be alert to these things that are happening right now, you know, and like quantum computing was one of them. And my favorite one is what's happening right now with the launch vehicles, right? That all of a sudden you might have, you know, increase the amount of, the cost of launching things might be dramatically less and large amounts of it. And I think that if that happens, and it seems that we're going in that direction, we don't know how to think about that. I think that we need to start figuring out, what do you do if somebody says, you know, you have 10 tons, you know, in the surface of Mars, you know, what would you do with that, right? I mean, we are so used to trying to minimize and reduce and increase costs, by the way. And how would our cost models work, by the way, if when mass sometimes drive our cost models, and sometimes mass should be able to let us do things cheaper because we don't have to engineer things. So that's one of the areas that that I hope people are thinking about in the area of technology. How do you use these new launch vehicle capabilities?
Mm-hmm. Maybe add to that and just say part of the challenge there is finding the right questions to ask at the right time, you know, and that's something that at the Keck Institute we try and think about those really forward-thinking ideas that maybe aren't ready for this decade or coming around now, but they could be in the future. We actually have a study that's taking place later this year that is touching on exactly what you've just said.
Really?
So, given this new era of super heavy lift launch vehicles that we're seeing coming online, what does that do in terms of enabling future sample return missions from across the solar system? So really trying to go back to the drawing board, bring together the right community of experts, again, across the science and the engineering domains, to think about that question with a completely potentially different paradigm shift in technology capability. And so I think there's some really exciting ways that you can encourage people to think about those questions in a different way, or maybe ask different questions that we haven't been able to ask previously.
Well, perhaps, Thomas, I could ask in this context, when you were with NASA SMD, what was going through your mind when you were making your selections as a selection official in terms of what's being presented to you as ideas for these large strategic missions and how you balance the science goals against the technological risk?
So, the kind of decisions come in both the competed PI class bucket and the strategic buckets. My personal feeling is actually that we have been taking a lot of risk on the strategic side, actually inadvertent amount of risks at times. James Webb is a good example. By the way, I'm not saying we shouldn't have done that. I'm just saying if you stood back and quantified the risk of a James Webb Space Telescope mission with its 10 technologies, before you add system kind of technologies, that's a huge amount of risk. The same is true with some others that are big missions. The PI class, so in this case, what you try to do, is try to bring the number of miracles down.
Yeah.
Because it kind of turns out, a miracle being a new technology, kind of something we don't know yet what to do. Of course, frankly, I don't want to be in the business of zero miracles. That's boring as hell. I always said, let's another agency do that. But if you have many miracles, the problem is they start interacting. So you have n miracles, the complexity goes with n squared. Like this problem over here starts coupling into this one, and that just becomes, so that would be the kind of thoughts you try to have and kind of try to isolate, can we do some of the things first. On the PI class missions, there, what I really felt, and remember, as the AI, you don't get to see all proposals. Right? There's frankly, you can't possibly look at everything. And then sometimes, I was in my awake hours at night, I wonder what did I miss that I didn't see, right? Because I think that is not a nonsense. Not because anybody tries to do something nefarious. It just, perhaps there's kind of ways people have leaned that basically take a whole set of solutions off the table so you never get to see it, because that's the wrong category before it comes to you. On the others, what I really felt was important is to not look at just risk by itself, but some kind of a ratio that had at the top the science benefit and at the bottom the cost times risk, right? And if the science benefit is really high, you can take more risk. So we actually had a number of missions, and frankly, we did not at times the lowest risk mission was also the best value, but that was not always the case, right? So, and frankly, and we talked about it, we also lived it that way. And I understand every AA, based on whatever the last problem was you had, is thinking about it differently. I talked to others, who basically said, you should really go for the lowest risk mission always. And I just really felt you should accept risk, but what you should also be able to do is terminate things. Yeah. Nobody wants to talk about that either. But you cannot create a thing that then eats your lunch. Nobody wants to become famous for terminating missions. But nonetheless, I think that's part of an innovation strategy that also needs to be talked about.
Yeah, and that's always, the typical risk item when you're thinking about if there's a key technological miracle that has to happen in order to make that ambitious science occur. It's a difficult question to answer. I was curious, Adrian, also from your perspective, working on Clipper, there are many instruments, of course, on Clipper, and we'll hear a little bit more tomorrow during the Pickering lecture from Bonnie Barati on Europa Clipper. But, since you're sort of down there, in the trenches, and of course, that's not a decadal mission per se, but it is a high priority science mission. Do you feel, in terms of the instrument that you're developing, and you don't have to answer this question, but do you feel from the perspective of the instrument that you're developing that it meets all the ambition that you had initially anticipated in terms of, everything you wanted to achieve with respect to its contribution to Clipper?
Yeah, so this is why I brought up that we know that there are always difficulties and always challenges. The plasma instrument is not the most complicated instrument on Clipper, right? It's very straightforward, Faraday cups, but still we did run into issues building it. So it's never, even when you think something's going to be simple and you have it down, you get these curveballs that then you have to address. Now, all instruments on Clipper have been delivered and they're all installed. So that part is over. We're launching on October 10th. But I do feel that with new technologies especially, we really, really need to be strategic and think about them well ahead of time because of, some of this experience with fairly simple instruments too on big missions.
So do you mind if I just add to this? There's one instrument on Clipper, it's called the mass spec,
yeah.
which was impossible to develop under normal rules, I would just say. I thought the team tried really hard, but it just spiraled, became really expensive. And what we did is we basically said, let's make it a tech demo, capped in cost, and just try it. And the answer is, it was developed within that cap, which I think is just incredible. Also there, I thought it was like 50-50, roughly. Yeah. Just like with the Mars helicopter, or with the chronograph on Roman, which I think, to me, is, if you look at technological complexity, that would be the example. It's in every way as complex as the helicopter on Mars, probably more. And for me, I just really wonder whether sometimes as science community, we miss modalities of development, right? If everything needs to be absolutely perfect, and it absolutely needs to work, you have no wiggle room. I actually think, that, I always said, like, if, in fact, Europa spurts some of its liquids out into the environment, this mass spec will make everybody famous, even though it was the tech demo on the group. Of course, your instrument will be an important part of it, as will others. But nonetheless, it's kind of, so just, I wonder, are we thinking about it broadly enough that we can, or are we self-limiting because we just squeeze everything through the same tunnel? So
we are our worst enemy sometimes, right? And when we pursue that perfection, sometimes we ended up doing the opposite, I think. I think that we ended up with systems that are not as good as if we were, sometimes it's our own decision, right? Just to take a little bit more risk and really concentrate on the important aspects, of the problem. I've seen it happen, I've been working on all types of missions in Pathfinder where we were allowed a lot. It kind of I believe that the ingenuity is a little bit what we had in Pathfinder, where the fact that we were giving, the possibility to fail, we were able to, I believe, achieve in some areas more reliability when we tried to do too much of a good job. It's a point of not just that, diminishing return, of negative returns. It's a psychological thing. I don't know how to fix it. But that's a clever trick right there, just turning into a demo.
Just to tie these things back together, I really liked when you said that we need lessons learned and incorporate lessons learned from previous technologies and what was proposed, how did that work out. I also think we need lessons learned from missions that we know went over budget. And I think when these concept studies are being developed for the next decadal, then we need to give them guidance on, yes, consider these lessons learned and demonstrate how those lessons learned will be implemented in the mission concept.
Yeah, that's a good point. I mean, many of the decadals now are introducing these decision rules, sort of in that context. I think it's an important point. I do see there are quite a number of questions here. Let me just pose one or two of them. So here's one. Is there a need for a cross-decadal or cross-discipline common technology portfolio? And would this leverage technology dollars more effectively?
Well, there are certain aspects of spacecraft that you're always going to need electronics and computers and most of them solar arrays and stuff. So I would say yes, why not? I think that we should have cross-cutting disciplines that go across all the different decadals. I don't know how to do that, but I think that is something that should be looked at.
And of course, the Space Technology Mission Directorate has, in part, as part of their job, to kind of implement this kind of work. I think one of the things one could consider is how to better tie it into the cross-decadal type of work, which I think at times has not been done at the level that it could be. It's not because people aren't trying hard and are being successful with many things. It's just because kind of in many ways it comes from a different perspective and perhaps it has more political wing. Like kind of the decadal is an anchor in kind of against political forces, which I think has been positive because we finish missions. We don't just start them. We finish missions and fly them, right? And so kind of that anchor, the question is, how could Space Tech Directorate benefit from that? I believe, for example, in quantum technology, which is not so clear where it should go, because quantum sensors, let's say, I think every discipline will benefit from it. I mean, you look at, the planetary, but also astrophysics and heliophysics, frankly, and earth science too, measuring water below the surface. In reservoirs is a really important measurement that, we're using a technology now that's quite complex. With the right quantum sensors, we possibly could do it better. So for me, just sitting at NASA headquarters, and it's like, wow, we're not making progress enough. And then it's actually hard to figure out who to blame, right, other than me, because I don't know who to blame. See, it's like, we're like, why are we not? It's so clear it's going to be important. I don't know how important and where, but like every time we've looked at nature in new ways with an entirely different process, it's just like our eyes have been opened in an entirely new fashion. So it must be important.
Yeah, I'm hopeful things like the high-performance spacecraft computer, will open up, new regimes of questions and science that can be done with that increased onboard processing capability. And we've seen some of the benefits with the Qualcomm processor on Ingenuity and what that might mean for the science we can do.
I wonder, have that data been published? How few hiccups that software had and that hardware? I want to see these data out. The hiccup data, that the overall radiation impacts were much lower than of the rad-hard side of the systems. Again, for me, that's what you're talking about. Lessons learned. Let's talk about that.
Yeah.
Like we tried, and it's like, hey, it works amazingly well. I looked at the numbers, and I'm like, we need to publish that. Go publish it, Charles.
Okay, I will take that as a homework assignment.
Good idea.
By the way, if I'm wrong, say I'm wrong.
No, that's true. Miguel, you might know, but the last I had heard after, I guess, the 72nd flight was there was one highly likely upset that occurred.
That's what I heard too. So it was very infrequent, essentially. Yeah. And people are looking at now I hear, at least at JPL, a new, wave of, looking for applications even on what we call high reliability missions. So it's, and that's kind of interesting, right? Sometimes, like ingenuity, sometimes you go solve a problem and you solve another one, right? So in this case, if the major thing that ingenuity does is to bring us into changing our minds of how we use these COTS electronics, that would be a tremendous thing.
Yeah. I mean, one interesting question here is, one of the significant challenges that we have is generally poor understanding of how much work it will take for enabling technologies to be ready for mission infusion. There's too much unacknowledged uncertainty, and that just brings up more risk. So the panel's asked, are there any ideas on how to get a better handle on this question? The question of significant challenges dealing with the uncertainty of the technological
That's a
readiness.
topic that I'm very passionate about. I mean, the TRL levels, right, is supposed to be the thing that tells us how much risk and resources it's going to take to finish the job. And it's a very, very dull, weapon. It's just, and we all recognize that right? But that's one of the problems, right? There are certain technologies at TRL level 6 that doesn't mean anything in terms of how much effort it's going to take to bring it all the way to flight, right? So, and I think that's part of the problem is that we don't have a good way of quantifying that. What's the remaining risk? How much? What are the resources that you need to put into breaching that? The rest. And there is also I noticed this in the technology community. There is this feeling that if you got to 6, it should be flyable. Everybody's saying that, if it is at 6, people should go and fly my technology. Say, wait a second, not all TRL level 6 are created equal, right? So I think that there's a lot of discussion that needs to. I feel that that's, at least in the technologies that I've worked in, is the part that I feel that is so frustrating. I mean, we flew TRN, Thomas, Terrain Relative Navigation in 2020, but that was not an easy process, right? I mean, just finishing that gap. The technology risk has retired, right, at that point, but still was the development risk was still there, right? And so I think that that's something that is it's a big problem, I believe. I mean, in the Decadal Survey, we pointed it out. We called that a second valley of death, which I don't think is as recognized as the other valley of death.
Well, there are many questions here, but I only see we have just a couple of minutes left. Maybe I'll just ask if any of the panelists have any initial thoughts with respect to this question. I mean, in terms of what I think I'm hearing, I think there's definitely a role that technology capabilities could have to influence scientific thinking, but unless there's a real mechanism to communicate to that community well, what the readiness is of that capability, what specific, new transformative science would be created as a result of that capability that would overweigh other mechanisms through which important science questions may be asked or proposed. It could be hard to, definitively decide, what should or should not, or what may or may not drive either the science questions or the technology that should be advanced. But it does seem like there is room for these communities to find mechanisms to perhaps interact more efficiently and to, I would say, try to jointly come to some viewpoint on how you can balance and advance the capabilities in both areas, both the science and the technology. Because from, as I mentioned earlier, from my perspective, having been on some white papers, I was often brought in to comment on the technology capabilities that are being proposed to explore the science mission, never brought in to say, hey, what's out there that we should be aware of that may help drive the types of questions that we may want to address further, and what is its technical state of readiness, and what is the risk in our proposal process in putting this into a white paper, and how are we going to get it to the committee in such a way that they would take it seriously. And just again, turning to Harriet, I'm hopeful that organizations like KISS or others that create an environment for people to have those discussions could have a more prominent role in terms of the way in which people prepare their white papers and present their ideas to the academies and have the community discussion to ensure we're, being as ambitious but as safe as we can be in all these scientific areas.
Yeah, and I think that combination of bringing the science community and the technical community together is really key. There are potentially different priorities and objectives from each side, but I can see that tension can also be complementary if channeled in the right way. It helps on both sides to maybe think about things from a different perspective, or challenge in a way that you might not have otherwise thought, right? So you've just kind of touched on that, right? Is there technology that will enable science questions to be answered that you might not have been able to think about before? Or, are those science priorities giving more focus to technology developments that maybe don't have that direction that is needed, right? So it's really, I think, in bringing those two communities together that you can have that magic happens, where you have more progress than you might have originally realized that you could have if you didn't have those conversations.
I would like to add something to that, and I know we're in
yes.
So, but since I'm no longer at NASA, let me just be a little bit more direct, perhaps, than I would have been if I was there. One of the things we're doing is we're somehow pretending we can manage things like some MBA and kind of manage technologies like we do some kind of spreadsheet somewhere. Kind of developing technologies of the type that you made a name for yourself, Miguel, and others, that we admire. They're like really scary and hard things. Mm-hmm. And what I'm really with Harriet to kind of let's learn about that scary and hard path, like we go hiking mountains. We do it not because it's easy. We do it because it's amazing once you're up there and it's worth getting there. Mm-hmm. But so many of the scientists sit kind of in their offices and think if an engineer cannot make something happen, it's because they're somehow inept. It's part of that thrill of developing the technology. It's kind of learning about each other, speaking each other's language, visiting each other's labs, I think will go a long way. And frankly, if I was running at Decadal, it's like, first we'll go visit some labs so you actually see what happens and how hard it really is. So part of it is just really understanding each other's language and really the understanding of what it is to actually develop technologies, but also the thrill of it and the tremendous benefit that comes from it.
Oh, absolutely. Well, thank you so much, and it's okay we ran over. I'm on the next panel. But I really appreciate that all of you would come here and talk to us on this topic and that you would engage with us through these questions. So thank you very much, and please stay in touch.
Okay.
Thank you.